We present Recovery RL, a new algorithm for safe reinforcement learning which can learn image-based and contact-rich manipulation tasks while effectively balancing task performance and safety. Safety is an important consideration when using reinforcement learning for robotic control, as uncontrolled behaviors and failures during learning can be dangerous to both the robot and its surrounding environment. Safe learning is challenging because to learn about safety, the agent necessarily has to experience or observe constraint violations to learn what types of behaviors are unsafe, and learning new tasks from scratch necessarily requires extensive exploration of the environment. This can often be directly at odds with safety, since safety requires limiting exploration. In this work, we will design an algorithm inspired by recent advances in safe RL and control theory. In particular, we draw inspiration from recent works that define safe regions of the state space for learning policies, where safety is inferred based on the ability to complete the task, robustly avoid constraint violations, or reset the environment to the starting configuration. In this work, we will define a safe set that is based on the discounted future probability of constraint violation under the current policy. To take a step towards addressing these challenges, we consider the following design goals for Recovery RL. Can we endow the agent with information about constraints before it interacts with the environment? And can we encourage safe exploration without significantly sacrificing task performance? We can achieve these goals by leveraging offline data which contains examples of constraint violations to learn about the probability of constraint violation in different regions of the MDP, and by learning two policies which each specialize in different ways: a task policy whose only goal is to maximize the original task reward, and a recovery policy whose objective is to reduce the task policy's probability of constraint violation when it is in danger of violating constraints. This mitigates objective conflict between exploring sufficiently to learn new tasks and constraining exploration enough to remain safe. The offline data can be collected by a human or an agent under human supervision to provide controlled examples of constraint violations, such as gently tipping over a glass rather than aggressively knocking the glass over and shattering it. Thus, the agent is able to observe constraint violations and learn from them without the task policy directly having to experience too many uncontrolled or extreme examples of these violations during learning. Recovery RL works by first leveraging offline data collected by some behavior policy to learn a safety critic, Q risk, which estimates the probability of constraint violation under this policy. Then, an action is sampled by the task policy at the current state. If the sampled action is considered unsafe under the safety critic, the recovery policy is executed to protect the agent from constraint violations. Otherwise, the task policy is executed. The task policy, recovery policy, and safety critic are all updated online from agent experience. In simulation, we evaluate Recovery RL on 3 2D navigation domains, 2 contact-rich manipulation tasks, and 1 visual navigation domain. In our experiments, we consider the following questions. Can Recovery RL effectively trade off task performance and safety? Does offline data enable safer online exploration with Recovery RL? Can Recovery RL be applied to visual motor tasks on physical robots? In all learning curves, we report the ratio between cumulative task successes and constraint violations, which quantifies how efficiently Recovery RL trades off between task performance and constraint violation. We find that Recovery RL significantly outperforms other state-of-the-art safe RL algorithms across all domains considered, suggesting that Recovery RL is better able to balance task performance and safety during learning. Here we present some qualitative examples of recovery behavior in the navigation domains during learning. In particular, we observe that the agent almost reverses direction when it is near an obstacle or wall and heading toward it. This zigzagging behavior indicates that the agent is switching off between the recovery and task policies. We also ablate various components of Recovery RL and study sensitivity to the number of transitions used in the offline dataset, and find that offline data is critical to Recovery RL's performance, but that Recovery RL is relatively insensitive to the number of transitions used. Finally, we evaluate Recovery RL on a constrained image-based reaching task on the Da Vinci surgical robot and find that Recovery RL is again able to outperform prior algorithms while effectively balancing task performance and constraint satisfaction. In this task, the robot must guide its end effector to the target position in green while staying out of the red region of the workspace. Breaking down the results further, we observe that Recovery RL is able to both successfully complete the task more often and have fewer constraint violations during learning in the first 150 episodes. In future work, we will investigate how to train the task policy and recovery policy jointly on an offline dataset so they are better calibrated with each other when online training starts. We will also evaluate Recovery RL on additional image-based physical tasks where contact is necessary, such as peg insertion. In summary, we present Recovery RL, an RL algorithm that leverages a set of offline data to learn about safety and constraints in the environment. Recovery RL separates task optimization and constraint satisfaction across different parts of the policy. Recovery RL outperforms state-of-the-art algorithms on a set of 6 simulated and 1 real domain, including contact-rich manipulation and image observations.